Good afternoon, everyone, and welcome on the session that will be devoted to crack with tension chord model in the compatible stress field method, basically in the Ideastica 2D detail. My name is Lucas, and I work as a product engineer in the company Ideastica, and guide you through this presentation and article. Just a brief intro. We just submitted new article on our website, knowledge base article that is named crack with tension chord model verification. And this article will in detail describe you how Ideastica considered the calculation of the cracks, uh, leveraging the tension chord model and stabilized cracked pattern. Okay, so before we just started off, the basic equation or the assumption that this that we will be spinning around is this equation. To calculate this equation, you need to have some inputs that's are coming out from the theory of tension chord model. But this fundamental equation is basically staying behind everything. Yeah? Uh, what is very important to understand is that the equation is also published in the Eurocode 1992-1-1, where this equation is basically mirrored uh, with some slightly elegant different shaped or different form, but you will exactly see this part of the equation there for calculation of the crack width. So what is inside the equation? As you can see, this is just the integral in between the cracks. So at first we need to pump, or not the cracks, but the crack spacings. So at first we need to map the crack spacing, calculate basically the integral. Here is the x direction, and based on that, we will just get the magnitude of the crack width. So it makes sense to start off with the explanation of the epsilon m, which is the average strain in between the or on the rebar. So if you imagine that you have just the bar that is submitted to the tensile load, and the bar is encapsulated inside this cylinder. So in there will be happening some cracks after exceeding some tensile strength in the concrete. But at first there is some crack spacing. This is this SR S subscription R, where it's dependent on the diameter and the effective reinforcement ratio inside the structure. What about the bond stress? So as you can see at the end, or at the conditions where the cylinder is basically cracked, so the bond stress is basically dropping to zero. Otherwise, in between the cracks, we can see that if we make it uniform over some regions, so we can see that some bond stress is increasing into the middle or a center point in between the crack spacing. What does it mean? This is the biggest bond is basically in between the cracks, and the bond is dropping down after you reach the yield point. So if we are staying before um, before the yield point, we are on basically on the elasticity of the rebars. So that is just the consideration that the um, interaction in between the concrete and reinforcement rebars is guaranteed by this 2 times FCTM, and the FCTM is mean tensile strength in the concrete. So there is just utilized the magnitude 2 times if we are just going over this threshold, basically going on the plasticity. So that's starting to drop to FCTM. Based on that, you can see that this is the trend of the stress on the rebars. So that's basically dropping down into the center point in between the cracks and gives you a lower value on the reinforcement rebars. So the approach that is implemented in the CSFM is to make it averaged. So and using the epsilon m, so we just make the averaging in between the cracks, and based on that, this is the first input to this equation. As you can see, there is just the contribution of the tension. We consider, because there is just the mean stress or average strain, I would say. So we are using also the average contribution of the tensile strength in the concrete that is stepping into the equation, and this is like 67% of FCTM, and epsilon cm is basically this value. This is introduced here in this part of the equation. So this lambda is 2/3 times the FCTM, and here is ECM. Yeah. So this is how it works, and basically we have two inputs for calculation of the crack width. So before I just move forward, let me explain just a little bit how the numerical model is assembled behind. We have some reinforcement bars that is meshed independently um, in comparison um, with the 2D plane stress plane stress model of the wall of the concrete. So thanks to the fact that the reinforcement tree bars is modeled independently as the concrete, we are leveraging the bond element that has some initial stiffness, and also some limit tau characteristic K. So this is the bond strength, and has also some GB. This is the uh, shear stiffness. So based on that, this is some coupling elements that in the bottom nodes we are utilizing some multi-point constraints that are linked into the or mapped into the nodes of the 2D plane stress concrete wall. So based on that, it's guaranteed the redistribution of the localized, displacement or forces from one node uh, to like a coupling nodes. Okay, so this is how it works, and we can basically move forward to the two main parameters for calculation of the crack widths. Um, Not two but three. The key parameters: effective reinforcement ratio, crack spacing, and the average strain that is basically linked with the reinforcement ratio. So in the first step, what we need to do, we need to have some algorithm that will be mapping the number of the reinforcement rebars and also the effective tensile strength uh, around or in the vicinity of the reinforcement rebars. So if I will just take the calculation of effective reinforcement ratio, this is just the area in general uh, divided by effective area of the tension in the proximity of the bars. So this is how it's affected, or reinforcement ratio, how it's calculated. If we have just this first step, we can move forward to the second step, that is just the fundamental calculation of the crack spacing. So what's you need to do? You need to have diameter, FCTM, and effective reinforcement ratio, and in the denominator there is just the tau b0. If we just come back here, so tau b0 is basically uh, equal to 2 times FCTM. So this is my assumption. If you have it and if you put the effort and filling out the equation, you will receive the same value as in the Idea Statica 2 detail or basically in the CSFM. If you have it, we can just move to the set of the equations for calculation of the average strain epsilon n. That, as I was mentioning, this is dependent on the interval that is calculated. So for each interval, you can find out that there is like a different equation that is calculated. So if you take a matcat or Python, whatever, and you will just filling out all the values there with the um, correct conditions, you will receive the epsilon m. So this is the average strain on the rebars that is basically coming out from the stress in between the cracks minus this bond in between the cracks based on the thresholds. Yeah, so there are just the thresholds that you can observe. Okay, so this is, I do believe that those are three parameters that's been explained, and we can move forward to material diagram and of the reinforcement rebars, how this material diagram um, is phased off in this or is mirrored in the inputs for uh, numerical simulation. Okay, so material diagram. At first, on the vertical axis, there is just the stress in between the cracks, sigma SR. In the horizontal branch or in the horizontal axis, there is just the epsilon m, that is the average strain. I will just start off with a simple pure steel linear diagram where you can see you are just hit the yield point and you have some linear hardening with some modulus with some modulus plastic modulus of the elasticity, and you will reach basically 5% plastic strain and basically stop the analysis. So this is how it works if you have just a pure naked steel. uh, it works like that because there is neither effect of the tension of the tension stiffening or strain hardening, I would say. Okay, but based on that, if we just consider the tension chord models, I just made up the loop over the some reinforcement ratios from really low reinforced concrete to high reinforced concrete, and we can observe what is happening with the stresses, and we can observe what is happening with the strains. So the essential point is that the the point that is changing is mostly uh, at the I would say at the ultimate strength. What is changing is the strain. So all the curves for different reinforcement ratio, just the reaching the same strength. So you can see if I just draw the line like that, the strength Fu is 540 megapascal, and all the material diagrams are ended up at this point. But once we are talking about the ductility is reducing based on the reinforcement ratio. Once you have a lower and lower reinforcement ratio, the um, the reinforcement rebar starting to be basically more brittle and less ductile. So this is the principle of the reinforcement ratio, how it's affecting the material diagrams, and where basically the ductility is how the ductility is reduced. It's going it's also stepping into the crack spacing, where we can see the nonlinear trend that on the vertical axis there is just the crack spacing, and on the horizontal axis is reinforcement, effective reinforcement ratio. So once I have like more reinforcement, I'm just getting smaller crack width or crack spacing. I would like to just mention and highlight that the trend is basically non-linear or some exponential, not linear dependency. Okay, let's move to benchmark to outline how it works if you just do it in the CSFM or in the IDEA Statica 2D CSFM. So I just prepared the model, just the benchmark case that this is just a rectangular section, the width 250 and the height 1000 millimeters. This is basically the submodel. So I was utilizing the submodeling approach where, as you can see, I have some that's called sand but none zone or some trimmed end, where the simulation is not running. It's basically like a rigid zone. So the simulation here is not displaying, and on the left side is basically displayed. So this area is basically analyzed, and the area on the right side, this one, is providing you the load transfer or correct load transfer into the um, submodel where we need the results. So the results that are, or the loads that are applied, is just the normal force that is uniform over the length of the submodel, and the reinforcement rebars are distributed equally. So there is everything is centered. There is no shift in the center of the gravity. So you should receive the strain that is uniform and is going equally to all reinforcement bars. What's about the application of the um, of the forces? So what you are doing, you are just applying the force here. So here is just reference point, and the reference point and the end of the edge of the San Bernard zone is basically mapped with this RBE2, what are basically the rigid links. Sorry, those are basically the rigid links. Okay, and this is some kinematic condition that is saying that if this node moves about 1 millimeter, the other nodes that are linked also move about 1 millimeter. Yeah, so this is how it works. And what are the outputs from the simulation? So if you just start off the simulation, you will receive some stresses that are uniformly distributed over the height of the section to all reinforcement rebars. There is just basic assumption that the material diagram for concrete, here is just the minus epsilon minus sigma, here is just the epsilon and basically sigma tension sigma tension. So in the compression, it looks like that, and in the tension, it looks like that. There is just the plasticity stopping at the 7%, but there is no tensile strength. So all it means that all forces should be transferred via these reinforcement rebars. Okay, so based on this assumption, if there's just a pure tension, we can expect that it will be strained equally to all reinforcement bars, and you should get the magnitude 9.5 times e minus 4. What about the effect? As I was mentioning, I will wrap it up. Effective reinforcement ratio, this is the value that is foundable in the auxiliary tab in the IDEA Statica CSFM in the auxiliary, I would say. So there is just the reinforcement ratio. This is the value. There is also another value that is like a geometrical reinforcement ratio, but this is not important for our case of the tension chord model. This is for another approach for calculation of the low reinforced concrete. It's called pull-out model or non-stabilized crack pattern. But right now we are talking about the stabilized crack pattern. So we are leveraging this effective reinforcement ratio. So as I was mentioning, the solution gives you the output in the form of the crack spacing that is also uniformly distributed over the length of the submodel, and the crack width, if you would like to calculate the crack width, so you've seen that there is in the first page there is some integral in between the epsilon m minus epsilon cm, what is the averaged contribution of the tensile strength in the concrete after or along the um, very small distance dx. Yeah, so it's just the integral in between the cracks basically, or in between the crack spacing that gives you the crack. What I would like to point it out is that for the calculation of the crack width inside the idea statica detail or in this 2D CSFM, uh, the crack width is basically calculated that you will take you will take the strain on the rebars, what is basically the epsilon m, and you will just multiply that by the value SR0, and you will get the 0.2163 millimeters. So this is how you get the crack width. As you can see, the one part from the equation, this epsilon cm, what is the contribution of the uh, concrete in the tension, is disregarded for this case. So this is the reason that the contribution gives you for this case approximately 3% reduction of the crack width. So that's dismissed for this solution, and you will get a little bit higher cracks, what is basically on the safe side. Okay, so this is the approach for calculation of the crack width. If I will move forward, I just pressed out the diagram that is stepping into the simulation for reinforcement bars. So again, on the vertical axis, there is just the stress in between the cracks. On the horizontal axis, there is just the average strain. We can see that for our purpose, for the effective reinforcement ratio 1.72%, this is our case, our reinforced submodel, you will receive the maximal strain, basically the epsilon m, that is explicitly expressed by this equation, 0.019. So this is my maximal strain that is quite far away from 5% plastic strain that is for an egg steel, because the egg steel is like a continuously going forward. And as you can see, here is this effect of the tension stiffening. But the threshold, as I was mentioning, FU is always the same for all the levels of the reinforcement ratios. You need to reach the maximal strength on the rebar. Hand calculation. So this is the proof that everything is working well and is well established and well developed. So what you need to have some like inputs. These are the stresses that are basically those are data that's It's our line spacing in between the from 0 to 400 to 550, and the step is one megapascal. So you will get the list basically of those stresses, and based on those stresses, you were calculating the relevant strain, and you can just outline the sigma SR and epsilon M like a diagram. Yeah, so you will exactly know that this is how your diagram looks like inside the idea statica. So at first, what I need to do, I need to calculate the crack spacing. As you can see, the value is 229, and 229 was also the value displayed in after the solution in the CSFM. So this is the fundamental crack width, S with the subscript R0. If you have just the S with the subscript R, as you can see, this is the averaged crack spacing, because here is the lambda, and this value is coming to all the equations that are here. So this is the reason why we are just considering average strain, average strain. Uh, okay, so once you have it, we can just move to the validation uh, of the results. So epsilon m, or average strain for value 245. This is basically the output from the simulation. So you can see that's here, 245. You will receive 9.5 times e minus 4. So if you just input this diagram to the simulation, run the simulation, and you will receive, and you would like to double check, if you just insert the value, you should receive the same value 9.5 as in the output of the CSFM. Here is the epsilon s. The epsilon s is just the pure naked steel diagram. Okay, so this is something like that, and the epsilon m is the diagram with tension stiffening. What I did, I just insert this 245 to show you what is the contribution of the basically strain stiffening once the rebar is embedded inside a concrete. So this is basically 23%, I would say, strain stiffening on the rebar. You know that you're because you are here somewhere. So this is 0.0012, and epsilon m is 0 or 9.5 times e minus 4. So this is the part of the strain stiffening. Once we are approaching to crack width, the tension cord, this is the equation that I was just mentioning before, is the average strain times the fundamental crack spacing, and you will get 0.2165. In our case, the output from idea statica, 0.2163. This is the contribution of the tensile strength, or average tensile tension in the concrete. So once I will utilize and put the effort and the equation, um, and I will just add this part to the equation, and I will subtract it from the average strain and multiply it by the fundamental crack spacing. As you can see, I will just receive a little bit lower crack. And if I will do this deviation in between those two values, this is basically 3.1%. So the contribution of the tensile strength, or average tensile strength, in between the cracks is negligible. So that's also not activated for a standard version in the idea statica. So let me just take some conclusion. So key takeaways, some fundamental assumptions for serviceability limit states, that the bond in between the reinforcement three bars exists, and it leads to the in general, incompatibility in between the strain fields and strain fields for rebars and the concrete elements, because the bond elements ensuring the coupling in between those two parts. So there is just the slip is ensured because there is just some stiffness of the bond element. The average strain gives you some tension stiffening that is passed to the material diagram of the reinforcement rebars. Three critical parameters that are affecting the crack width is the effective reinforcement ratio, average strain, and crack spacing. And for tension chord model, as I was mentioning, the contribution of average tensile strength, this epsilon cm, is neglected for the calculation inside the idea statica. So the crack width is in general epsilon m minus epsilon cm, epsilon epsilon cm times SR0, and this member is neglected, and crack widths are calculated uh, independent with with epsilon m and SR0. So the deviation is approximately 3% if you calculate it with or without. Yeah. So I do believe that you enjoyed the session, um, and that we build up the trust in you, and you will be very confident with leveraging and utilizing idea statica for calculation of the serviceable limit states. If you just come up with some questions, do not hesitate to contact the help desk of idea statica with the queries. We will very friendly help you out.